and from a Babylonian text on how to heal certain types of wounds. Oh, that's right. That's right. It was in History of Science, Williams and Steffen's History of Science. Yeah, Pierce Williams and Henry John Steffen's History of Science in 3 volumes. And I read to them some stuff from these ancient texts, and they asked them, they said, would that work to do those things? And I said, no, that's why people died all the time. I read this to them. I said, listen here, if a man go to the house of a sick man, and a falcon goes along at his right, that sick man will get well. If the falcon goes along at his left, the sick man will die. If in the morning, in the rear of a sick man's house, a falcon proceeds from an enclosure at the right to an enclosure at the left, the sick man will speedily recover. If in the morning, in the rear of a sick man's house, a falcon proceeds from an enclosure at the left to an enclosure at the right, his sickness will be protracted. If in the morning, in the rear of a sick man's house, a falcon flies away, the sick man will die. You've got to watch out for those falcons. It's pretty gruesome. We could go on and read more of it. But read some of that stuff to the kids. They thought it was crazy. Starting out with the Greek scientists, the Ionian philosophers and stuff we'll get to later. I went over them a bit, but a lot of it is so heavily theoretical, you know, the Ionian revolution. So we're skipping that and going to the golden age of science, and I can teach them stuff like the laws of levers and stuff, and then give them a deeper run-in with Greek science next time around. One interesting fact with Archimedes was his law of levers. The law of levers states that weight times distance equals weight times distance in a balanced lever. So if you have 1 inches on this side of your fulcrum and 8 inches on that side, then you need, for example, about 8 pounds over here, and all you need over there is 1 pound. 1 times 8 is 8, 1 times 8 is 8. So that would balance. So we could also make that up of extremely fulcrum right there. We could put 2 inches there and 10 there, and 50 pounds here. So 50 times 2 is 100. So X is the number we need to find what we need on the other. 100 divided by 10 is 10. So if we put a 10-pound weight there with 10 inches, it would just equal a 50-pound weight with 2 inches. You can play around with that and stuff. And this allows the building of a really fun toy called a trebuchet. It allows us to understand it. The Romans and the Greeks never built trebuchets. They used catapults, which use torsion. Trebuchets use gravity. They use a really heavy weight at one end. So you pull this down, this lever way down, and this weight goes way up in the air, and then you tie something onto it there, and let go, and it slings and flies. And Archimedes allows us to do calculations with our trebuchets. And so we built a few trebuchets. It's a fun project anyone can do at home. It's done out of cardboard, some Tinker Toys, and some old bolts and wrenches. And I'll just give you a demonstration shot. It's all caulked and ready, and I've got this trigger right here. And it has wheels so it can roll back and forth a bit. Pretty fun machine. You just have ammunition. It usually has to have some sort of a string or something attached, and throw those babies. And here's a slightly larger one, also made out of 100% cardboard. This one, however, has a swinging weight on the end, because when you release, it falls. It tends to try to fall in the straightest line possible, pulling the trebuchet forward, as it would if the trebuchet were fixed. It would have to arc inward. See its line arcing inward there. But ideally, it would want to fall straight down, and if it can pull the trebuchet forward an inch or so, it can keep that forward, keep that downward motion instead of turning it into sideways motion. And give more power to the shot. So a rotating bucket with what I call a Archimedean supercharger on there, which stops it right there. Otherwise it would hang down, it would hang straight down, you know, clear there at the top of the arc. But it sticks out a little ways, an Archimedean supercharger. And we went over that with the kids, why an Archimedean supercharger would supercharge it. So, interesting stuff we're doing in science. Learning about the history of medicine, which is going to run us into learning about the golden age of Islam and stuff, the fact that they were taking people's cataracts out, or doing whatever happens to cataracts, whilst the people in Europe were just living in little huts and stuff. History of medicine, science, and astronomy, 3 different areas, and you know, science as such, but then there's 2 subsets, which are astronomy and medicine, being taught along with science. Now then, some things have occurred to me about Ptolemy, and the kids are going to be ripe for dealing with the modern physical theories when they have to later on. They're going to be ripe for them because we're talking about Ptolemy and epicycles, and the fact that Copernicus, who made the sun stand still, was not able to give as accurate results as Ptolemy was with all of his epicycles and equal points and stuff. So that Ptolemy predicted things that were going to happen, you know, as far as astronomy goes, more accurately than Copernicus. Even though Copernicus's theory was more accurate as per reality. And so the kids are learning the 4 steps from the Dark Age to the modern scientific era. And the 4 steps are Copernicus, Galileo, Kepler, and Newton. And I have these names up on the board, and I have the kids write down the years. Even the really young ones who are too young to really get too much out of it, the 2 youngest ones, they write down the names, the years, and a little catchphrase. And here's the catchphrases that I had. Sun, stand still! Exclamation point. For Galileo, catchphrase is that he proved Aristotle wrong. Now, just a brief note, the kids don't even know Aristotle's name really yet, except for a couple notes like this that has happened. But I haven't gone into Aristotle as such yet. I feel we're just about ready to dive into him, though. But just, you know, his scientific writings in biology and different stuff that he said about the Earth and heavens and the moon and stuff. Alright, so Kepler said there are oval orbits. And then Newton said, pardon me, gravity. Copernicus actually used epicycles still. He actually had to use epicycles to slow the planets down and speed them up. People weren't sure why planets were slowing down and speeding up. But Copernicus died before he was able to figure that out. Handed it on to Galileo, who didn't get it either. But he invented the telescope. He discovered that the solar system is changing. He moved it one step further. He also said, well, look here, there's a lot of work we need to do in physics, isn't there? Because Aristotle was wrong about these heavy and the light ball thing. An experiment that had been done a couple of times before Galileo did it. But perhaps Galileo catches the imagination most because he did it on the Tower of Pisa. Galileo comes along and says, let's work with physics a bit. Kepler says, you know, we could get the planetary motions to work just right if we used ovals, but he didn't know why an oval would happen. It's like everyone knew they were working in perfect circles ever since the Greeks. And Kepler says ovals work better, but no one could say what's going on. Why does a planet move in a weird shape? That's ridiculous. It should just go in a circle. Well, then Newton came along and said it works that way because of gravity. And when it's going, falling towards the sun, it moves a bit faster, and then goes out, slows down, getting away from the sun, and then falling towards it again in that oval shape. Those are the 4 steps